Hello, welcome to this introduction to deep reinforcement learning. Today we will see how tabular reinforcement learning algorithms can be scaled up to applications in games and robotics. It's easy to see that we cannot apply tabular methods to most of the interesting applications because the discretization of a larger state space grows the size of the table exponentially. This is sometimes referred to as the curse of dimensionality, and there is not really a good way around it. This is very unfortunate, because it would be so cool to have an AI that takes, for example, images as an input, like playing the Atari video games. So how can an AI learn to play games like these without any in-depth knowledge of the game's implementation? Well, you all have heard of the magical power of machine learning. So maybe we can just replace the table of Q values with a neural network? Since our input is an image, we use a convolutional neural net here, as shown, which has an output for every action we could take. For Atari games, this is moving the joystick in 8 possible directions with or without pressing the red button. We will interpret each of these outputs as the Q value of the corresponding action for the input image, which we interpret here as the state of the system. So for every transition in the environment, we could simply make a gradient descent step on the regression loss of the TD error. Sounds easy, right? Well, it's not. The problem is that Q-learning violates basic assumptions of the supervised regression. For example, regression requires both the samples and the regression targets to be drawn IID from stationary distributions. This is not the case for the TD error, where the regression targets change when the network parameters change. Exploration also changes the distribution of encountered states all the time, and updating transitions as they happen does not sample them IID either. To make DQN work in practice, we need to use a bunch of tricks that stabilize learning. The most important are to first draw mini batches of past transitions from an experience replay buffer to get IID samples. And second, to compute the regression targets with a slowly changing target network. This makes the algorithm much more complicated and is often more an art to get it to work in practice. However, current versions play all 57 Atari games better than the average human, which is pretty impressive. Okay, so far, we looked only at discrete actions. But in many applications, the actions are actually continuous. For example, if the stick puppet here wants to walk, the state of the puppet is the angle and momentum of every joint, and the actions are motor torques. These are continuous, and it is not clear how we can find the action that maximizes any given Q value function. Instead, we will learn a neural network policy, which outputs an entire distribution over actions. For example, we can model a Gaussian distribution by learning the means and variances with a neural network. But how can we learn the parameters of this policy? It turns out this is possible even without learning any value functions. We only need to maximize the expected return starting at the first state. The gradient of this return can be computed as the expectation of the weighted gradient of the log likelihood that the policy would have selected an action. For a formal proof of this, please have a look at the Sutton and Barter book here. The policy gradient therefore reinforces actions that lead to good returns, which gives the algorithm its name. Reinforce needs to sample a number of trajectories for every gradient update step, which makes it slow and in practice also not always very stable. However, modern variations of this algorithm, like PPO and SAC, are much faster and learn surprisingly efficient controllers for simulated robots. To summarize, In this video, we have learned that tabular reinforcement learning does not scale to large applications. We have shown that Q-learning can be scaled up to play video games, at superhuman levels even, and how the reinforce algorithm can learn neural network policies for continuous action spaces. However, be careful when you are applying these algorithms. There are significant differences between reinforcement learning and supervised learning. As DeepRL is still an active research field, make sure you are familiar with the newest literature before you try to use it in your work.